Welcome everybody to Contemporary Math Hybrid. This is section 2.1 on set concepts, and we're going to take a look at some examples that you might run into talking about set concepts. So in our first section, we're trying to determine whether a set is well-defined or not well-defined. So again, a well-defined set has only one interpretation. So in our first set, it's all of the real numbers. Okay, because mathematicians can all agree on what a real number is, this is a well-defined set. Now in letter B here, it says X is a good singer. So this word good right here is open to interpretation. Not everybody will come up with the exact same set. So this is not well defined. Alright, letter C. So X is a member of contemporary math class. So there is an enrollment, there's actually a roster of students in the class. So this is well defined. In our next example, X is a skillful runner. So that word skillful again, you have to ask yourself, what is skillful? It can mean different things to different people. And so this set is not well defined. In our next set of examples, we want to determine whether the set is finite or infinite. Okay, so this is dealing with the cardinal number. If the number of elements in the set is a cardinal number, then it is finite. So here, the number of integers between 2 and 7. So sometimes it's helpful to figure out, can we write them all out? So this would be 3, 4, 5, and 6. So the number of elements here is 4. And because 4 is a natural number, we would say this is a finite set. Now, of course, that's a very technical definition. You can look at this set and see that it stops. Okay, contains a finite number of elements. Now, in our next example, 1, 3, 5, 7, comma, dot, dot, dot. Okay, those 3 dots, that's the ellipses, and it means it continues on in the same manner. So we would get 9, 11, 13, and it keeps going. And notice this will never end, so we can't put a natural number to it for the number of elements. So we call this one infinite. We will deal with infinite sets a little bit later in this chapter in section 6. So be on the lookout for that. Now our next set of examples is actually writing out sets. Okay, so what we have here are set descriptions, kind of just made out in words, and we want to put this in roster form, much like the roster on a team. And we do this by putting them inside braces. So we're going to list all the elements inside a set of braces. So we have the curvy part, the pointy part, the curvy part, and you'll get better at writing these, or if you're using a keyboard. We want the natural numbers less than 4. So remember, natural numbers are the counting numbers. So you start counting at 1, 2, 3, 4, so on and so forth. So we want all of these numbers that are also less than 4. So that's just going to be 1, 2, and 3. And then we close out the set with another brace. So it's curvy, pointy, curvy. The next one, set B, is a set of natural numbers less than or equal to 80. So we're still going roster form. So we open up our brace, curve, point, curve. Natural numbers, so they're going to start at 1. Now, if we wanted to write out all 80 numbers, we could. Okay, but it would take a lot of room here. So instead, what we're going to do is use an ellipses to continue the pattern we've started. So 1, 2, 3, that establishes our pattern going up by 1, and then all we have to do is put our ending number 80, and then we close our brace. So we're going to assume that includes all of the elements there. The next one, set C, is the set of natural numbers between 5 and 8. So this word between does not include the 5 or the 8. So we would actually start at 6, go to 7, and then stop. In letter D here, set D is the set of natural numbers between 5 and 8 inclusive. So that word inclusive means that we're going to actually include the 5 and 8 in our set now. So we would get 5, 6, 7, and 8. Okay, so that's how we take a description and write it in roster form. For our next examples, we're actually going to be taking sets in roster form and writing them in set builder notation. Now, this is a very mathematical way to do it. We're going to use some x's or variables and possibly some equations as well. So here we have set E, and it's 1, 2, and 3. So anytime you write in set builder notation, it's always going to start the same way. Open your braces, pick a variable. Usually we'll just be boring and pick x. And then we put a line. Okay, and they're always going to start this way. So this is the set of all x's such that, and now we have to give some stipulations. So we're going to give two different points here. The first one is, what type of numbers are these? What set do they belong to? Well, those are counting numbers. And so we're going to say x is an element of the natural numbers or counting numbers. So that's the first part. Say what type of set they come from. Then we're going to be specific. So which of the counting numbers do we have here? Okay, and this can be stated as x is less than 4. So what we have here are the counting numbers less than 4. Now in this we could have also written x is less than or equal to 3. And that would have described the set as well. For our next one, now we have 11, 12, 13, 14 going up. So again, we're going to start all set builder notation with x such that, and we see what type of numbers are these, what set do they belong to. So these are counting numbers. So we say x is an element of n. And here we have 11 and up. So I can say x is greater than or equal to 11. All right, moving on. For the next example, it says write the following in roster form. So here we're going to take a set builder notation and translate it backwards into roster form. So we see x is an element of n, so we're only going to write natural numbers, and then we just have to figure out what this inequality means here. Okay, so here's our set A. So x is greater than or equal to 3, meaning we're going to start at 3, and then it's less than 9. So we're going to go up to not including 9. So 3, 4, 5, 6, 7, and 8. All right, in our next example, what we're going to be doing is finding NA for each set. Okay, so that is a symbol that you're going to be seeing a little bit here. And what we're doing is we're looking for the cardinal number of the set. And all we have to do is count the number of elements in the set. Okay, so for this first one, we just count 1, 2, 3, 4, 5, 6, 7. So we would write NA equals 7 because there are 7 elements. In letter B, we might not want to count these because it goes all the way up to 1,000. So we're going to look at the pattern here. It goes 2, 4, 6. So we're taking all the even numbers up to 1,000. So half the numbers are going to be odd, half the numbers are going to be even. And so we're going to do 1,000 divided by 2. And we get 500. So here, the number of elements in set A is 500. Now for our next set, we have x, and x is the set of integers between -10 and 9. So remember, the word between does not include the -10 and 9. So sometimes it's helpful to write these things out. So we have -9, -8, -7. Don't include 10. So let's count these up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We actually have 19 numbers there. So the number of elements in set A is 19. Now sometimes the set will not have anything to do with math at all. This one is the set of current U.S. senators. So sometimes you need a little bit of knowledge to be able to do this. So we think we have 50 states, and there are 2 senators per state. So 50 times 2 is 100. So the number of elements in set A is 100. In our next set of examples, we are going to be dealing with elements or non-elements. So we're going to try to see if certain items are members of a set or not. So in the first one, we're going to say, is 5 an element of the set that contains 2, 4, 5, and 6? Well, if it's in the set, then 5 is an element of that set. Okay, in our next one, 8. Is 8 in here? Yes, it is. So 8 is an element of the set. Our next one, -4. Okay, we don't find -4 in this set, so we make the element symbol and then just cross through it. So -4 is not an element of the set. Our next one, -12, is not an element there. 0. Okay, 0 is in that set. So we're going to put the little element symbol. And the next one, 0, is not found in this set. So we're going to put the not element symbol right there. All right, moving on. For our last set of examples here. Now we're going to be dealing with determining whether sets are equal, equivalent, or have one-to-one correspondence. Now the first set right here, we have A and B, we have K, C, R, and A, and then K, C, A, and R. So for two sets to be equal, they have to have exactly the same elements. Now it turns out that order doesn't matter. Okay, so here I see K and K, that's the same, C and C, A and A, R and R. There's nothing extra. Okay, and there's nothing missing. So these are going to be equal. Now, are they equivalent? Okay, well, equivalent just means they have the same number of elements. Well, if they have exactly the same elements and are equal, then they're automatically going to be equivalent. Then, does it have one-to-one correspondence? So all this means is, does each element match up with another element? Meaning, is there a first element with a first, a second with a second, a third with a third, and a fourth with a fourth? Okay, so in this case, they do all match up, and if they're equivalent and have the same number of elements, they're automatically going to have one-to-one correspondence. So if two sets are equal, it automatically makes them equivalent as well as having one-to-one correspondence. Now let's look at our next set. Here we have E, H, A, and N. Here we have A, H, E, and Q. So by looking at these, because of the N and the Q, these are not equal. Okay. But since both of them have 4 elements, that makes them equivalent. And if they're equivalent, we know we also have one-to-one correspondence. In our next example, here we have 5, 8, 9, and 0. Here we have 5, 8, and 9. So in our first one, the number of elements in set A is 4, and the number of elements in set B is 3. When the cardinal numbers don't match up, they are not equivalent, and they cannot be equal. Okay, so here it has none of the attributes. Okay. In letter D, we have 3, 7, 12, 14, 3, 7, 12, and 0. So they're not equal, but because they have the same number of elements, they are equivalent and have one-to-one correspondence. All right, and E and F gets a little bit more tricky. Now we have some set builder notation and some roster forms we're trying to see here. So here we're going to evaluate this. X is a counting number less than 3. Is that the same as the set that contains 1 and 2? Okay, so counting numbers less than 3, that's 1 and 2. So these are equal, which makes them equivalent and have one-to-one correspondence. Letter F, X is a counting number greater than 10. So counting numbers greater than 10 are 11, 12, 13, so on and so forth. And you can see that as the exact same set here as B. So these are equal, equivalent, and have one-to-one correspondence.